All right, good morning, everybody. That was a really inspiring keynote. I'm also really excited about the GraphQL Summit. We've seen so many talks about why GraphQL is great, why people are using it, but we haven't seen that many talks on how people use it and the problems they've hit and the actual solutions they found. So I'm really excited. I already talked to a few people here when we shared problems we encountered in our solutions. So this talk is going to be two parts. The first part, I'm going to talk on how we build tools and solutions to some problems we had on the server side for GraphQL. And Dylan's going to talk about, on the mobile side, kind of the same thing, how we built smarter clients for mobile. So my name is Marc-André. I'm from the cold Montreal, Canada. And I work, obviously, at Shopify. So Shopify is an e-commerce company. We basically make it easy for anybody to sell things on the internet. And like many companies, we've had and still have REST APIs. And we had the same pain points that maybe a lot of you hit too. So our clients were making way too many round trips to get the data they needed. They way too many round trips. It was hard to customize what data they were exactly getting. The way we did field filtering was a little awkward. So we wanted to explore something else. And a few months ago, we played with React Native a little bit at Shopify. And although it wasn't perfect for our use case, we kind of discovered GraphQL through it. And fast forward to today, we've just released our mobile app that's powered entirely by our GraphQL API. So me and Dylan both work on the GraphQL core team. And our goal is really to make it easy for any team to build their own schema or extend the existing schemas. So we're getting pretty large. We have a lot of developers working on platform. We have many teams that might want to create a new schema or extend existing schemas. And we also want to make it easy for mobile developers to maybe extend the schemas too. So the first thing we tackled was how will we define our schemas and execute GraphQL queries for the Shopify API. And the first thing we did is turn to the open source community and found a great GraphQL gem that maybe some of you use. And we especially found a great maintainer, Robert, so shout out to him. He's been really helpful, really responsive. So with that gem, it lets you, like many other libraries, define your types, define your fields, arguments, with a nice little DSL you can see here. But keeping in mind that our goal was to make it easy for really anybody to extend it. And we have a gigantic Rails app, monolithic Rails app, and our developers are really used to a certain way of coding, and we thought maybe this was a little too far from what we were used to. So what we did was actually build kind of two different abstractions on top of that gem to help us make it even easier. So we have the GraphQL gem that we use to execute these queries and define the internal GraphQL types. But we also have what we call graph model on top, which helps us define these types with another syntax. And Graph API, which is a layer that really contains more of the Shopify-specific stuff. So this is what our graph model layer looks like. It's quite similar. It's class-based. Types are defined using simple symbols instead, and we have explicit keyword args for nulls. So it's pretty straightforward, too. And we're a Rails shop. People are used to active record. You might have noticed the syntax before kind of looked like active record, too. And we wanted to kind of push it further and really make it easy for anybody. So we have helper methods like belongs to, which in the end just defines a normal field, but you don't have to have knowledge of how to define that using GraphQL syntax. We have so many other helpers like cache as many, who's going to take care of fetching that from memcache, for example, or a paginated helper that's going to define a relay connection for you. So it's been great for helping people just really extend our schemas. But naively building a schema using these still result in some problems sometimes. So let's take a look at this query, for example. I want to go through the execution of that query and just take a look at what kind of calls are made to fulfill that query. So for example here, we might have shop here. That's going to select shop for our MySQL. We're then going to fetch products, which is also pretty simple, as we're just fetching products where shop ID is 1, right? But if you go down to the image resolver here, turns out it's going to be called 3 times, and it's going to do 3 queries in MySQL. And that's a little awkward. That's not necessarily what we want. And the reason why it's doing that is each resolver is actually called in different contexts. So maybe if it was in the context of like one controller, obviously we would have maybe like preloaded that data so we don't only do one call. But our results are actually called in different contexts. So each resolver doesn't know how many other images are going to be loaded. So we could have went with a solution of maybe analyzing the query and trying to guess what calls are going to be made so we can preload before. But it's really complex, and maybe we didn't need something like that. So we went with the usual solution of patching. And we've actually released a gem called GraphQL Batch, which Dylan is the main maintainer. And it's really great, and the principles are actually quite simple. And you might be familiar with the principle if you use the JS server too, this famous data loader that a lot of people use library. It's pretty much the same principle. So the principle is to, instead of returning the value right away, the resolver can actually just return a promise for that value. And a loader, for example, is going to take the record class, maybe it's going to be product here, and an association, which was the image we wanted on. And when we load for a particular record, we don't actually fetch the image right away. We just indicate we're interested in that image at some point. So the same kind of image as before, instead of returning the values in each resolver, we're actually just telling our loader that we're interested in each of these 3 products images. And inside an actual loader, it's pretty simple too. We have the load method that we just talked about, caches, remembers, and returns a promise. And we have a perform method that's called only once, and will actually do the hard work of patching that query. This example here is our memcache association loader, which is going to prefetch the images on a certain set of products and fulfill every promise at once. The hard thing here is when to call perform. If you've used data loader, you might know they use a little trick that you can do in JS. They actually wait for process.nextTick to enqueue their perform promise. But we were in Ruby, so we couldn't really do that. So what ended up happening is we used promise.rb to return these promises, which is a promise A+ implementation in Ruby. And we use a custom executor. So basically, when we get the result from the Ruby gem, we actually look for promises and resolve those. So we actually know that every possible promise was enqueued. And we have a nice API for that too. So all that logic is actually hidden behind a keyword arg. You can just say, for that field image, just please preload it. That should be field product, actually, preload images. And what that does is basically wrapping the normal result for your field with a prefetch proc. So before hitting the resolve, we're actually waiting for that promise to be fulfilled. So that's been really helpful to hide the complexity behind batching and helping really anybody stop people from basically shooting themselves in the foot with these queries. So if we take a look at the same query, but with batching this time, we're going to have the same queries, except this time we're actually going to batch it. So this is great. We have other thing too. For authorization authentication is another kind of pain point people are often hit when using GraphQL. And one of the solutions proposed is often having it in a resolver itself, checking for the user, what they're able to do. But we went with something a little different. Our API clients, access tokens, already have the concept of scopes, so resources they're allowed to access. And we actually collocated that with our type definitions. So for example, an order type requires access to orders. And we can actually say, write, if you're allowed to write, or is it read-only? Or we can even specify for a particular object, is the API client allowed to access this type? And we compared that against an access control object that we passed in the context. And that access control object contained everything about the API client, its capabilities, what types it can access. But there's still stuff that we need to protect ourselves against, like evil clients that might build like really complex queries. And there's many solutions to that, like query complexity, calculating like a score for each field, maybe a max depth. But we went with the simple solution of a timeout, and we use just Ruby timeouts class, which will raise after a certain amount of time. Another thing that clients might attack us with is just like really a lot of queries. And we've reused the same thing we had with our REST APIs, which is just a simple throttle. It's like a leaky bucket throttle, which will raise to if an API client for a certain key. The key might be a shop ID in our API client. We're going to throttle it. So that's helped us mitigate some of those bad clients. But really the cool thing that I really like about our Shopify implementation is really the developer experience around building and extending schemas. So we always checking the IDL of the schema in version control, so we can actually really see easily what's being changed on a schema, breaking changes, and we enforce that. So if we compare the new schema against the old schema, and if you change the type, change the field, we're going to ask to rebuild that schema dump and check it in. And we pay really careful attention to not breaking the schema for no reason. So when you try to generate the new dump, if something has changed and it's creating a breaking change, we can detect that and instruct either you really want to break it or maybe rethink what you just did. So we also have on GitHub, we have a bot that's going to alert our GraphQL team whenever the schema changes. That also helps us maybe like help somebody who's new to GraphQL that might have just added a field. And we also have a strong set of conventions. These are just a few examples. Our mutation actions, we always prefix with the object name instead of the action. This makes it like a little easier for us to like find mutations since we have a lot. Our mutations return the user errors for errors that should be shown to the client. And we support the relay spec always. So we have actually tests that will check for these. For example, did you forget the client mutation ID for a mutation? We might instruct you to rename mutations. And we have a few other things too, like instrumentation. Instrumentation is really important for us at Shopify, and GraphQL wasn't different. So we currently have any errors, the throughput we have, query time, the clients that were throttled or timeouted. We really want to have like more precise instrumentation, so we're working with Robert, the author of the GraphQL gem, so we can have maybe nicer hooks to instrument actual resolver times and things like that. So we also have deprecate field usage tracking. So every time a deprecate field is executed, we actually log it, and we're able, using a tool a little bit like Logstash that we use internally, we're able to actually query for these deprecated fields, and it makes it really easy to know when we can safely remove a deprecated field or not. So that was a subset of what we have currently on the server side. And there's so much more, so feel free to come talk to us after. But for now, I'm going to let Dylan come talk about what we did with our mobile clients. So please welcome Dylan.
All right, so first I'm going to give some background on what we were actually building and help you understand why we built what we built and how we got there. I'll talk about how we use code generation in order to build the clients that we built. And I'll also talk about how we do caching, and more importantly, how do we keep data consistent across the app when it changes. We were rebuilding the mobile Shopify app. We were told we need to rebuild it so it provided a full Shopify admin experience rather than a limited companion app. So we decided to make sure that it was also fast on slower networks, so we changed the tech stack as well, and we looked at GraphQL as a way of reducing the response sizes. We managed to ship it in time for our deadline, which for us was because we wanted our merchants to have it before they were busy with the holiday season. We started by building it in React Native. We found it very quick to build out the app, but we had some troubles with making sure we can polish it and get it to the quality that we wanted. So we ended up deciding that since this was a mission-critical app and we weren't sure if we could get the quality we wanted in the time we wanted, we ended up going with native mobile SDKs. So that meant writing Java and Swift, and also meant we had to leave behind Relay, which is in JavaScript, unfortunately. It was a hard decision, but let's see what type of goals we had with building the new GraphQL clients. We wanted to keep it simple. At this point, I'd already worked on building out the server side, so we had something there, but we needed something on the client to query it. We didn't just want to specify literal strings, which would be ugly, or deal with the raw JSON directly. We also wanted it to be easy to understand for our mobile developers. They're the targets. They're the ones actually using this. So we want to embrace what they're used to, which is a static type system and IDEs. So we wanted to fit in well with that. And we want to think of what's going to happen after we actually ship the app. We need to make sure we can evolve the schema, and we want to be able to add to this over time. This initial release is just the point where we can replace the companion app we had before. And for us, that meant decoupling the code, so using components so we can easily add components to it. In order to do all this, we realized the GraphQL schema was the killer feature for this. This is what I think Facebook really developed this schema for. They wanted it to integrate well with static type system. So we used that for code generation. We built code for building a query and for the response classes. And we wanted to make it easy to use. So we have a script that doesn't require any arguments to use, and that only has to be run in order to take advantage of anything added to the server. So let's look at what the code generator produces for us, starting with the query builders. On the left, you can see the code for building the query, and on the right, the query it actually produces. Notice the similarity between that. That's on purpose. We use the builder pattern to implement this, where we add fields by calling methods, which are chained by them returning the object they're called on, and we use closures to specify subfields on those. We use literal values in order to specify any arguments, which are provided when we're building the query. So the query is actually built at runtime. We have a similar API for Java, and at the time, we thought it was going to be hard to provide this because Java 8 had Lambda expressions, but there was no support for that on Android. But we found out we could use retro Lambda to backport this to older versions of Java. Now there's an Android toolchain which we might adopt when it's more mature, called Jack, which also provides support for this. Normally, it seems like fragments are used for composing queries, letting components specify what they want so they can keep their data dependencies close to their data use. We took a much simpler approach. Instead, we just have a function that takes in a query builder object, and we can put that on the component, and it can specify what it wants. And we don't have to have any more support for it or explain anything to our developers because they know how to do function calls. We do use fragments, inline fragments, in order to specify what fields we want on a specific object type when we're dealing with an interface. In this case, event is an interface, and type name is automatically queried on that, which we'll use in the response classes. We also automatically query ID, which you'll see that we use in the data consistency layer. By generating these type-specific query builder classes and methods for each field, we integrate well with the IDE because we can actually check these at compile time, but just compiling the code. And the IDE, since it can check for compiler errors, can highlight any errors for us. We also get auto-completion for free, and by generating documentation, we can surface that in the IDE. We also have deprecated field use by using annotations for that. So we kept things simple by leaving out some GraphQL features, and by integrating with the type system, we were also able to get all the IDE features without having to implement an IDE plugin just to provide that. We also were still able to do the loose coupling that we wanted, even without these features. And as the schema changes, we just run a script, and we can adapt to that. And notably, in order to remove fields as we evolve the schema, we can just mark them as deprecated, and when they run that script, they'll get some warnings for deprecated field use and can easily address them. Let's look at the response classes, because we don't want to deal with raw JSON. Instead, what we get to deal with is something much more pleasant. These response objects are already validated when they're constructed. They'll deserialize the fields and provide access to their methods so that we can leverage the type system. Notably, dealing with nulls is a common pain point, so we use Swift optional types, which allow us to be forced to check for null when necessary for nullable fields. And for non-null fields, we don't have to be concerned with, can this thing be null or not? That's all encoded in the schema for us. We found this so convenient, we decided to replace the model layer. And for this app, it made sense. We wanted to keep as much logic as we could on the server, and that way we didn't have to worry about avoiding code duplication. And notably, we can leverage all that code that's already written on the server and allow it to change over time. Since we wanted our response objects to be convenient, that also meant looking at custom scalars. We didn't want to deal with the string as it's encoded in the JSON response for money or date-time types. So instead, we took an approach of keeping our GraphQL code generator generic, so it'll work on any schema, but providing a way for it to be used where custom scalars can be. We can pass in something that can specify how to generate code for it. So in this case, we specify what type to actually use for it and how to serialize and deserialize it. So our update schema script is what adapts to our specific case for that application, whereas the code generator is separate from that. And ideally, we can open source it in the future. Another thing we have to address is the fact that we don't know all the types that are ever going to be there. We generate code, and we're going to ship the app, and people are going to run with old versions. So that means you have to deal with the enum values that we don't know about when the code is generated. To address that, we generate an unknown value and add it to the enum type for the language, like Swift or Java. And in the case of exhaustive switch statements, we can be forced to actually have a case for that, as well as being forced to handle all the known cases if we choose to use an exhaustive switch statement. For interface fields, we return the object type for the actual object and make sure that it implements the interface. But that means using the type name and making sure that we can actually match that with a corresponding response class. So we have to deal with the unknown case again. So we generate an unknown class for each interface type. So in this example, for event, we have an unknown event class, and that implements the event interface. And that way we can fall back to using the common methods on common fields on that interface. So in summary for the response classes, we simplified things by avoiding a handwritten model layer. We integrated well with the type system, and we left room for schema evolution. And in addition to that, we left room for the business logic to change without having inaccuracies by just being able to add fields to the schema that are computed fields. And we use that liberally to keep code that we classify as business logic out of the client. So let's end by talking about how we cache things and keep data consistent across the app. For caching, we cache whole responses, and we key that based on the query string and persist that to disk. That way, when the app is reopened, we're able to quickly render something, and if that data is changed, we still actually send that query so we can get back the response and change the view with the actual data that's we've just gotten. So we have to handle both of those responses, and we have a handle relay query method that's defined on a relayable object, which is an interface. And we pass that relayable object to the method to query for the data. So that handler method will get called multiple times. And we also keep that relayable object around in a list of active queries, which represent all the parts of the app that will need to be updated when data changes. And we have a weak reference in order to clean up that list of active queries when anything in it no longer is there to update, when the view's gone away. When a mutation happens, we want to update the whole app so that we can see that change represented elsewhere, and even as they navigate through the app. So what we do is we find all the nodes on the mutation payload and match that against nodes in the active query objects in order to find everything that needs to be updated. And we match those by just comparing the IDs. We deep merge the fields from the payload node onto the active query node, and then call that handle relay query method in order to update the view. Optimistic updates are similar in that they target a specific node and specify what action to perform on it, like deleting it, or we might do an update. For the updates, we use the response class in order to specify that, and have setter methods so we can specify what changes on those. When the response actually comes back, we want to roll back the optimistic update because we don't want to assume that that actually happened. It's just to present what we think will happen before the actual response comes back. So we kept things simple. We just have a whole response caching, and we use type checking for optimistic updates. And I think we built something for the long term by making sure that we have data consistency without coupling, which means when we do a mutation, we don't say, here's all the things that need to update. We just do the mutation and let the updates propagate. If this talk has been interesting to you, you can follow our work on our engineering blog. And it was pointed out that some people are hiring GraphQL devs, and I could certainly use some help. And hopefully we can open source some things that we've been working on here, at least the generic parts of it. Thank you.